Hello, this is Shaun Thomas, and today I'm going to go over project 4, the machine learning regression classification, and I'm working with Arturo, and I'm working specifically on the regression models. So first, I'm going to go over my data set that I chose. I chose this job salary prediction data set, and the goal with these models is to take in all these columns as inputs and predict the salary. So we're using regression classifiers, so we can predict a number on this continuous uh, I guess, list of choices. So we don't have classes for we're not assigning classes essentially. So what we're doing here is we're predicting a value on a continuous plane um, compared to selecting class from a predetermined list of available options. Um, so the first thing I want to talk about is my data set. So here we have job title, um, and this is a non-numeric value, and so is I believe I have a list of the non-numeric values. Education level, industry, company size, location, remote work, and job title. Um, so these are all converted into numeric values so that we can run machine learning models on them. And like I previously mentioned, we're taking all these as inputs and getting the salary as the output or the predicted output. So each of these different fields will have some sort of impact on the predicted output. Um, so next I'm going to talk about the machine learning models themselves. Um, so the models that I selected were linear regression and random forest. So what that linear regression kind of works is that it has it it's kind of like a linear classifier where it tries to draw a line that um, different points should try to be close to. So it gives respect to each input value and kind of gives weights to them. And then those weights, their actual values kind of determine like where they are on the graph. So some weights might have more importance than others, which determines where the eventual spot given its inputs will be on the graph. Um, as you can see here, it wasn't very accurate. I suppose that would be because of the inputs not being as maybe not being um, as important or being more important than the linear classifier predicted or assumed. Um, but on the other hand, random forest, which is the other model that I used, performed much better. And random forest essentially is a very complicated decision tree. So it looks at all the inputs and looks at different values that an input could be. For example, if salary is greater than or equal to 100,000, or if a job title is software engineer or AI machine learning engineer or whatever, it could possibly be greater than or equal to 100,000, that sort of thing. But random forest has a lot of decision trees inside of it, and it takes in an input value called depth. And depth essentially is the maximum amount of trees that it's allowed to make. So the more depth you have, the supposed better decisions can be made, or I guess more um, impactful decisions can be made. So that's sort of the models that I'm using. I chose the linear classifier or linear regression model specifically because it was one of the easier ones to use, and it's simple. So it's easy to get a baseline and understand how complicated the data set is. Like I said before, it performed pretty poorly compared to the random forest model. Um, but it was almost a near instant inference, whereas the random forest took a lot more time, or it's not a lot more time compared to other models, but like 3 minutes compared to a few seconds for linear regression. Um, there wasn't much parameters that could be messed with. There wasn't hyperparameter tuning or anything going on here. Um, just the default scikit-learn parameters were used. Um, for random forest regressor, I initially started out with 10 depth level, and that performed better than linear regression, but still not very good at all. Then I moved to 20 depth, and that um, improved the quality a lot better, um, about 96%. And I would assume if we push the depth up even further, we could get a lot better accuracy as well. So there's the models that I worked with. So now I'm going to go through the results summary. Um, so the first kind of data I want to show is the predictions versus the actual data. Um, I guess these are hard to read because they're all numeric values. Um, but as you can see here, if you compare like these first few values to these first values, um, they're off by a noticeable amount. Whereas where you compare these values to these values, they're off, but they're a lot closer to what these values are. So these are the error margins, or these are the um, validation. And here's the error margin using root mean squared error as a metric. So for linear regression, we had the R squared value of 0.4613 compared to 0.963 on the random forest model. Um, and then mean absolute error. So essentially, we're off about by 21K for the linear regression model, um, which is pretty noticeable if you consider that we're looking at data sets of like 100K to maybe 200K here. So 21K is very noticeable um, for this data set. Um, and that's same goes for 27K as well. But again, for random forest, we're getting a lot better values, 0.963, 0.9693% for R squared value. So this is really bad. This is a lot better. This could still even be better. But this is still notice better than this, obviously. And then for this, we are off by about 5K. Um, and here we're off by 6.5K. And again, that's not perfect. It can be better, but it's definitely a lot better than this. And this would be easy to get if we just up the depth level. Um, and then here we have these two graphs. Again, this is the predicted line right here. So if the dot is on the red line, it's predicted perfectly pretty much. Uh, as you can see here, the predictions are a lot more accurate on the random forest compared to the linear regression model. Um, so yeah, the linear regression model, I guess that maybe some input values it weighed too heavily or didn't weigh heavily enough, causing salary outputs to not be accurately predicted. Um, whereas for random forest, we're getting a lot more accurate values and a lot more consistency. Um, and then I guess the mean absolute error, as you can see, the blue dots aren't very far from the red line if they're not on it. Whereas here they're significantly far um, away from the red line or off of it. Um, so now I'm going to go through my result summary. Um, so like I mentioned before, I chose linear regression because it's simple to use and easy to get started with. And um, obviously, it didn't work out as well as random forest, but even the fact that it shows that we need a more complicated model to use has some value. It shows that our data set inherently is complicated and we can't use a simple solution. So even though we didn't get what we were looking for, we I guess we gained the knowledge of knowing that we need complicated model, and thankfully we have the random forest regressor. Um, this one, oops. This one was a better model to use. Um, the downside compared to linear regression is that it took a lot more time to use, around 2 to 3 minutes compared to just a few seconds for linear regression. But the results were a lot better, and it was easy to tune the parameters. Um, it was just literally just one variable for max depth. Um, so that's the models. So the results I already went over. For random forest, we got 96% using R squared compared to 46%. And then for mean absolute error, we got around 21K off compared to 5K off. Um, and then for root mean squared error, we got around 27K off compared to 6.5K off. Um, so yeah, this it shows that uh, random force is a lot better. So the result's acceptable. Random force is definitely acceptable. It can definitely be better. Um, but again, linear regression wasn't a good selection for this use case, as the data set was just too complicated and complex. Um, Random forest is the best model to use here. Um, I guess all the decision trees that work under the hood for this model are able to capture the complexity and significance of each data point from its input values and get the um, predicted output more accurately. Um, so yeah, random forest was good to actually get the value that we're looking for. Um, and then I guess also linear regression had the purpose of showing that our data set's actually complicated and we need a more complicated model. Um, so for recommendations for if I were to do this project again, um, I'm glad that I chose linear regression as a starting point before moving to other complicated models. Um, and I'd keep probably using linear regression. It's very simple to use and takes almost no time for inference before using more complicated models. In this use case, it wasn't particularly helpful for actually predicting things, but it was helpful for knowing that we need a better model. So I'd probably do that again. Um, I would tune more deeply uh, for my um, random forest model, so that we can get better accuracy in our predicted outputs, instead of having to continuously run it to check each depth value. Um, and then be mindful of training time. Some other models I tried to use, they would take 10 to 30 minutes to train. If I just threw them out, um, as for this use case, it's not particularly useful when, again, random forest can do it in 2 to 3 minutes and get a very decent output. Um, And then another thing I can maybe try to do better is encode some of the categories better. Um, Again, maybe some categories are affecting the linear regression model more than they should. So maybe encoding them um, to be to not be so sensitive to the model. Like maybe job titles aren't as important. Maybe, for example, maybe a software engineer and AI engineer are making close to the same, or maybe there's um, some level of software engineer that's not quite caught in the value. Like perhaps there's two software engineers and one makes significantly more as they have like a higher, I guess, higher job title with less experience years. That might throw the model off. So I guess cleaning the data better up could definitely help the linear regression model. Um, and maybe in the future using different training validation splits could be better as well. Um, Maybe running models on multiple different validation splits. Um, and then yeah, maybe again just clean the data inputs to making sure that they're not negatively impacting the values of the models we're looking at, and there's no like huge outliers or anything that could um, mess up the models from learning correctly. Um, so I believe that's all the things I wanted to demo in this video. Um, so that was the Project 4 regression model for Project 4.